We're interested in bringing depth sensing capabilities to handheld battery-powered devices in an economical way. To that end, we've been studying what we can accomplish with a single photodetector and with a single light source that's not raster scanned. Codac is our signal processing framework for achieving both depth resolution and spatial resolution in this setting. Today I'll describe Codac and our proof of concept experiments. Codac is a new framework for acquiring scene depth information using only a single time-resolved sensor by exploiting the sparsity of natural scene structure. A depth map of a scene assigns to each pixel a value representing the distance from the imaging device. Codac allows us to capture depth maps with fine depth resolution and fine spatial resolution. Laser scanning, or LIDAR, is an existing technique that produces depth maps measuring distances to scene points one at a time, using either time of flight or triangulation. Spatial resolution comes from raster scanning by the light source, so spatial resolution is limited by the scanning time. Time-of-flight cameras avoid raster scanning by having multiple sensors. They work at video frame rates and provide the high range resolution required for many applications. However, a time-of-flight camera does not provide high spatial resolution because it relies on a low-resolution 2D array of range-sensing pixels. In this work, we propose a single-sensor, high spatial resolution depth camera that works by exploiting the sparsity of natural scene structure. We exploit a key fact about scene structure. The depth map is generally a less complicated signal than the scene reflectance captured in an ordinary photograph. This comparison is brought out clearly by comparing discontinuities present in the depth map of a scene to the discontinuities in a photograph. The depth map discontinuities correspond to edges of objects. A photograph generally has these discontinuities plus many more. Thus, while photographs are compressible, depth maps are even more so. Prior to our work, this compressibility had not been used to reduce the cost and complexity of depth acquisition. Our technique, Codac, is based on the time-of-flight range measurement principle. In a conventional TOF camera, an array of pulsed LEDs transmit an omnidirectional pulse of light toward the scene of interest. The light returning from the scene is focused onto a 2D array of range-sensing pixels using optical focusing. By measuring the amount of time it takes for a transmitted pulse to arrive at a pixel, the TOF camera produces a depth map of the scene. In contrast, Codac uses a pulsed light source to illuminate a spatial light modulator. The spatial light modulator selectively illuminates the scene with a randomly chosen checkerboard pattern by selectively blocking some of the light. All the light reflected from the scene is focused at a single time-resolved photodetector. This generates an electrical signal, which is in turn sampled and stored. This process of illumination, integration, and sampling is repeated for a small number of randomly chosen binary patterns. Finally, the time samples collected through this acquisition are computationally processed using a parametric signal processing framework to reconstruct the scene depth map. There are several challenges to making this seemingly simple depth acquisition process. The most important challenge comes from the fact that our measurements are not linear combinations of scene depths. For this reason, standard compressed sensing techniques fail to apply to our problem. To illustrate this challenge, consider illuminating the scene with a sinusoid. The light signal measured at the photodetector is a superposition of the time-shifted and attenuated sinusoids corresponding to the different points in the scene. However, extracting the quantities of interest, which are distances to various scene points, is extremely hard because the measured signal parameters non-linearly encode the scene depths. Since we integrate all the reflected light from the scene, this nonlinearity worsens with the number of scene points simultaneously illuminated. Without a novel approach to interpreting the measurements, little useful information could be extracted from the photodetector output. The superposition of scene returns at the single detector results in complete loss of spatial resolution. Our solution depends on a key observation about scenes. Most objects in a scene are composed of piecewise-planar facets. In this work, we operate under this assumption. Extending our method to curved objects will be a subject of future work. To illustrate the two key steps of our acquisition, consider a frontoparallel scene for simplicity. In the first step, the scene is illuminated with an omnidirectional short pulse using an all-on pattern at the spatial light modulator. We have shown in our paper that as an idealized pulse of light propagates through the scene, the light signal that is received at the detector, shown here as P of t, comprises three box functions whose locations in time correspond to the different object distances present in the scene. The amplitudes are proportional to the relative sizes and reflectances of those objects. The true pulse shape and the photodetector blur the parametric signal with an impulse response h of t, and the resulting signal is then sampled by the ADC. The signal P of t belongs to a well-known class of parametric signals, and it's possible to reconstruct such signals from samples taken at a sub-Nyquist rate. As we demonstrate, the first step of omnidirectional illumination only gives us the range information about the scene and does not provide any spatial information to form the depth map. To recover spatial resolution, we proceed to step 2. This involves illuminating the scene with a series of randomly chosen binary illumination patterns, followed by parametric deconvolution to recover the amplitudes of the box functions. Note that the time locations of the box functions do not change from step 1. Once we've identified the depth ranges present in the scene in step 1, we exploit a key separability property of the depth map. The depth map of a scene is a weighted linear combination of binary valued depth masks, which correspond to the spatial content at a particular depth value. When we project a pattern on the scene, the linear separability property implies that the amplitudes of the box function corresponding to a particular depth is proportional to the inner product of the projection pattern with the depth mask corresponding to that depth. This is true at every depth range identified in step 1. By projecting a series of illumination patterns, followed by parametric deconvolution, we form a linear system of equations relating the box function amplitudes to the unknown depth masks. In addition to separability, we also introduce a robustness constraint, which we derive from the observation that each pixel in the depth map must be assigned exactly one depth value. As a result, the sum of all the depth masks is 1. Now to summarize our two-step acquisition and processing. In step 1, we illuminate the scene with an omnidirectional light pulse and use parametric deconvolution to solve for the depth ranges present in the scene. In step 2, we use the range information obtained from step 1 along with the measurements obtained from patterned illumination to recover the depth masks. Finally, we linearly combine these depth masks using the depth values as weights to recover the complete depth map of the scene. Details on our modeling technique and its extensions to non-frontoparallel planar facets can be found in our paper. We corroborated our modeling and algorithms with proof-of-concept experiments. Our experimental setup included scene illumination from an infrared pulsed laser source, which was spatially patterned using a transmissive spatial light modulator. The light reflected from the scene was focused onto a single photodetector with 0.7 nanosecond rise time. The scene setup and the recovered 64 by 64 pixel depth maps for two different scenes are shown. We demonstrated that our technique works for both frontoparallel and general piecewise-planar scenes. We used only 205 projection patterns, which corresponds to just 5% of the number of pixels in the reconstructed depth map. This is a significant improvement over raster scanning in LIDAR and the 2D sensor array used in TOF cameras. We obtained sub-centimeter range resolution in our experiments. This is significantly better than the fundamental limit that would arise from the 0.7 nanosecond rise time of the detector if we were not using parametric signal modeling. The improvement in range resolution comes from the parametric modeling and deconvolution in our framework. It's possible to implement our technique using commercial off-the-shelf hardware. Our calculations show that we require a light source with megahertz modulation bandwidth, a speed that's common in optical communication diodes. The spatial projection is easily implemented using a digital micromirror device, which is something already commercially used in handheld picoprojectors. Our sensing system comprises a single photodetector coupled with an ADC with megahertz sampling bandwidth, which is also common in many commercial imaging systems. In summary, our proposed compressive depth acquisition framework demonstrates significant improvements in range and spatial resolution over existing TOF-based range imagers. We refer the viewer to our publications available online for complete details and analysis. We believe that our illumination and measurement techniques can be achieved with compact, off-the-shelf equipment. The algorithms can be run on a smartphone, so you may have depth acquisition in your pocket soon.